Okay? So here's what I end up with. I end up with the cosine of 4x equals, this would be plus or minus radical 2 over 2. That should look familiar, right? So we want to know, where does the cosine of 4x equal plus or minus radical 2 over 2? Now, this does make this slightly easier. Okay? It kind of compartmentalizes it, makes it so we're looking at this problem right here. Cosine of u equals plus or minus radical 2 over 2. If you can do it without doing the substitution, that's totally okay. Some people can. I recommend doing that just because making a substitution to make it look easier and then getting an answer, reversing the substitution to get it in terms of the original variable that you were working with, is a technique that's used over and over and over and over again in math. Okay? So if you practice it now, the likelihood of being able to do it well later on is much better. So let's take a look at this right here. We're talking about two things. We're talking about where the cosine of u is equal to radical 2 over 2. And when we change colors, we're also talking about where the cosine of u is equal to negative radical 2 over 2. Well, if we look at a picture on the unit circle, and however you like to solve these, use your calculator, use a graph, use the unit circle, draw a triangle, any one of those are fine. You should be familiar with all four of those techniques, and you should be able to understand them and at least do a couple of problems using each one. But let's say we do this using the unit circle, because we're used to thinking about the cosine in terms of the x-coordinate on the unit circle. I want the x-coordinate to be positive radical 2 over 2. Well, that happens right here. Let me change colors here. Happens right there. And it happens right here. Now, even if my triangles don't look right, as long as I label them correctly, this is pi fourths, and this is 7 pi fourths. Those both have a cosine of radical 2 over 2, an x-coordinate of positive radical 2 over 2. Any questions there? Okay, I could then write the answer sets for each one of these, because this would repeat every 2 pi, right? So 2k pi plus 2k pi. Everybody okay with that? Okay. The other one over here, if I went like this, because I wanted a negative radical 2 over 2, this is going to be, let's see, what have we got here? It's pi fourths for a reference angle. Got to be really quick at these, because if you're spending as much time as I'm talking about this, figuring out what that is, I mean, you haven't memorized the unit circle like you should, and you're crippling yourself for this class and for 1060. So that's going to be 3 pi fourths, and this is going to be 5 pi fourths. Am I right? How often do those repeat? Every 2k pi. Any questions there? Okay. Are these the answers? Okay, they're not the answers. Okay? We need to reverse the substitution. We need to set each one of these equal to 4x, and we need to go through and divide. But stop and think about this, because we ran into one of these the other day, and the questions that have been asked to me this morning, they all fall in this same category. Hey, I looked in the back of the book, and I had 4 answer sets, and the back of the book only had 1. Or I had 3 answer sets, and the back of the book only had 2. So look at the way that these answers are produced. Look at how often they repeat. Is there a common repeating pattern here? So if I started with this one right here at pi fourths, how far is it in between pi fourths and 3 pi fourths? Say pi halves. It is pi halves. That's amazing. Okay, and how far is it in between 3 pi fourths and 5 pi fourths? Pi halves. All of these have pi halves between them. So we could write down one single answer set that says u equals, let's start right here at pi fourths, and then let's add, let's see, k times how often they repeat. How far is it in between them? Pi halves. Okay? And then if we come over here and we say, well, look, the original one was about x's. Let's reverse the substitution. We get this. 4x equals pi fourths plus k pi halves. Go through and divide. I get x equals pi sixteenths plus k pi, what do I put underneath here? If I divide everything by 4, I times the bottom by 4 to get 16, times the bottom by 4, and I get 8. And that right there would be the answer set. So if you look at number 4, which one actually works? Definitely A. Does this one work? Let me show you a little trick. Everybody watching? because this could come in handy. I'm going to rewrite this in a way that it will be very easy for me to figure out what the next answers are. Like, in other words, how much I add to each one to get to the next one. Isn't pi eighths the same as 2 pi sixteenths? Yep. So if I plug in a 0, I get pi sixteenths. If I plug in a 1, I get pi sixteenths plus 2 pi sixteenths. What's 1 pi sixteenths plus 2 pi sixteenths? 3 pi sixteenths. That one will work also. They both do. Okay? Now on this, I'm proud of those of you that actually tried to solve it this way. You could plug this into the calculator and see if it works. I mean, that will tell you whether or not those are solutions to the equation. This is much better to be able to do this. Okay? Let's see. The other question was it 21 and 73? Is that right? Okay, let's take a look at number 21. Okay? I have a picture of this. Put it here. And 73 ugly. Oh, that's a great problem. You'll see a problem just like this in... No, you'll see a problem like that in 1060. Absolutely guaranteed. Okay? All right. So let's take a look at this one right here. Ideas? Okay. Don't divide. Move it to the other side. Okay? Because if I divided by that, it would take all the answers that it would produce with it. We'd lose some of the answers. So I'm going to write cosine cubed x minus cosine x equals 0. Miranda, what do you think you ought to do next? Starts with an F. Factor it. So we're going to take out cosine x. That's going to produce some answers. This is going to be cosine squared x minus 1 equals 0. You could do this a couple different ways. I prefer working with the math F word, so I'm going to continue factoring. What does this factor to? Cosine x minus 1, cosine x plus 1. You could change it into a sign if you wanted to. Okay. This is a good technique. Brandon, how did you factor that? What's it called? The square thing. Very good. It's called the square thing. It's called the difference of squares. So what I've got here is cosine x minus 1, cosine x plus 1 equals 0. So we actually have 3 equations to solve. We want to know where the cosine of x equals 0. We want to know where the cosine of x equals positive 1, and we want to know where the cosine of x equals negative 1. And you should be able to answer each one of those very easily. Those are on the unit circle. They're a piece of cake. Okay? Think about how to write the answers, because the way those answers appear are quite unique. I think you can condense a couple of the answer sets. Okay? Any questions there? All right. Did anybody do 73? Tried? Okay. Okay. Has anybody in here had a physics class? Okay. So here's what we've got here. It says a sharpshooter. Let me see if I can highlight this again. All right. A sharpshooter intends to hit a target at a distance of 1,000 yards with a gun that has a muzzle velocity of 1,200 feet per second. See the figure. Neglecting air resistance, determine the gun's minimum angle of elevation in order to hit that target. Okay. I think I lopped off some of the stuff below, didn't I? Nope, there's nothing. Okay. Oh, it just says that's the equation. Okay, perfect. What does R stand for? Range. That's how far we are, right? Okay. Anybody know what V naught stands for? Initial velocity, how fast the bullet's going to begin with. And what does the theta represent? The angle. Now, There are actually two angles that you could fire this at, neglecting air resistance and wind and stuff like that. Most people would fire it straight at it. Okay, anybody played Angry Birds?
Yeah.
Okay, when you want to hit something in Angry Birds, there are two angles you can do. You can do a really low trajectory, right? Or you could shoot it really high and come in and bomb it from the top, right? So even on a problem like this would be pretty amazing with a rifle, okay? We could shoot this way up in the air, wait about 20 minutes, that wouldn't take that long, and then it would come back down and it would hit over here, okay? They want us to find the minimum angle, which on this problem hopefully is pretty easy. There is one thing that makes this much more difficult though, because of the way they've presented the problem. Does anybody see what it is? They're in different units. Okay, you do get big numbers, but we can deal with that with the calculator. The problem here is they gave it to us in different units. Okay, so in feet, how far away is this? 3,000 feet. This is more than a half a mile away. Anybody here a sharpshooter? That is a long, long, long way. Possible. There are Army sharpshooters that are pretty good at stuff like that. Okay, but that is a very, very, very long shot. Okay, so the first thing we'd want to do is we'd want to say R equals 3,000. We'd want to say V naught equals 1,200. So we've got 3,000 equals 1 over 32, and then this would be 1,200 squared equals sine 2 theta. I'm going to take this and I'm going to flip it over and move it to the other side. So I'm going to have 32 times 3,000, and on the bottom I'm going to have 1,200 squared, and that equals sine of 2 theta. Now, if you were doing this using the ideas that I taught you in this section, what would we do right here? Yeah, well, here's what I'd do. I'd say U equals 2 theta. You could, okay? You also don't need to square everything out and multiply it out. If you wanted to type this into your calculator, sine inverse of, start a set of parentheses for the top, then divide by 1,200 squared, close the parentheses. That would give you an angle. There are actually two. We want the smallest one, so we'll just take the one the calculator gives us. And what does it say? 1.9?
Or 3.8.
Okay. This gives you 3.8 degrees. We're in degree mode. 3.8 degrees, but that is equal to 2 theta. So what do we want theta to be? We want it to be 1.9. Okay? Does that make sense? This would be much more complicated if I said figure out the two angles. What are the two angles that we could launch this bullet at and still have it hit the target? Be kind of fun.
Minus that from 90 degrees.
What's that?
When you minus 1.9 from 90 degrees.
Not quite. Not quite.
Because 90 would just come straight down. And if you minus that 90, that's still an angle of elevation that you're shooting.
It is, but I don't think it's quite the right answer. Okay?
It makes sense in my head.
Let's see.
Let
me think for a second. Yeah, so what you do is, this kicks out a 3.8, right? Maybe you could just do that. This is 3.8. That has the right sine ratio. There's another one that has the right sine ratio. It would be over here. So this angle, yeah, I think you could. Yeah, I think you could. So this would be 180 minus 3.8, and then you divide that by 2. So yeah, I guess you could. You could just take, because this is going to be 90 minus half of 3.8. Yep, that would work. Never thought about it that way. I think that would work. I'd double check it. Okay. I've got another problem that I do all the time in my trig class like this. Any questions there? Okay. How many of you are done with 5.3? Okay, very good. That's a tough section. Okay. Do you have any other questions? Are you feeling pretty good? Okay. When is the test on chapter 5? Test is on Friday. Okay? All right. See if the starter question is an identity. How many say yes? How many say no? Okay. Who can remind us what an identity is?
Reversible, right?
A true reversible equation. If this if this side's true, that side's true. The two sides equal each other if you plug in numbers where they're both defined, right? Okay. So let me show you an example that's very typical. Everybody watching? Is that true? Okay, now what I did there is I kind of like distributed the square root through to each one of the terms, right? Okay, I mean, that looks very reasonable. If we were to show that problem to 7th graders, they'd probably say, yeah, we kind of learned how to do square roots, and yeah, that looks like it's pretty good. But if you actually check, this side is the square root of 25, so this side is 5. That would be a 3 plus a 4. This would be a 7, and we all know that's not true. Okay, in Brandon's world, that's true, so stay away from Brandon at least for the day. So let's check and see. This looks like it ought to work, but in reality, very few functions, very few operations can be distributed like we can multiplication. There's no doubt if I did this, if I did 2 times x plus 7, I can multiply those through and I get 2x plus 14, and if I plug in the same number to both sides, those two sides would equal the same number. That would be an identity. Okay? As much as this looks like it ought to be true, it's not. And to prove that it's not, all we have to do is come up with an example like this one. It's called a counterexample to prove that this isn't an identity. We just need one counterexample. So let's pick a really easy number to plug in. Let's say x is equal to 0. This would be the cosine of pi thirds equals the cosine of 0 plus the cosine of pi thirds. Now, we don't even have to know what the cosine of pi thirds is in order to get this right. What's the cosine of 0? 1. So this is 1 plus, we do know what it is. Cosine of pi thirds is 1/2, and then this side would just be 1/2. So what we'd be saying here is that 1/2 equals 1 plus 1/2. And is that true? No. Not true. So in general, please lock this away because you're going to run into other things that don't distribute either. Okay? Trig functions do not distribute. It would be nice if they did. They don't. Okay? These two things together make the argument. They make what we're plugging into the trig function. They make the angle together. Okay? You can't just break those apart and find each one separately. Okay? There are very few things that work like that. There are some things that do, a lot that don't. Okay? So what we're going to talk about in this section is something called the sum and difference identities for sine and cosine. And I'll show you the one for the sum and difference identity for sine, or for tangent also. It focuses on those three. There are identities for secant, cosecant, and cotangent. They don't come up very often, and frankly, the ones that come up most often are sine and cosine. So those are the ones that we're going to focus on. Okay? So that's what this section is about, and I'm going to show them to you right now. So I want you to copy these down, and I want you to copy them down the way I write them. So this is the cosine of one angle plus or minus another angle. And I'm going to write the plus on top and the minus on the bottom. So here's what cosine looks like. And this is the way I think of it so that I can keep these memorized. Okay? I like cosine. Of all the trig functions, cosine's my favorite for some strange reason. Okay? And I find that a lot of people, cosine is the easiest one. Okay? So here's what it is. It's the cosine of alpha and then the cosine of beta. So because I like cosine so much, I'm going to use it twice. These are both going to be the same trig function. They're both going to be cosine. Okay? Then since I took the cosine and the sine, or cosine of alpha and the cosine of beta, Then I'm going to find the sine of alpha and the sine of beta. Find each one of those separately. Now, because this one's my favorite and these two are the same trig function, I have to use the opposite operation here. Because these two are the same, if this was a plus, I'm going to write a minus. And if it was a minus, I'm going to write a plus. Now, you can write these as two completely separate identities. Like you can write cosine alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. And then you could write cosine alpha minus beta, cosine alpha cosine beta plus sine alpha sine beta. But I find it easier to memorize and keep them just as these, kind of put them together with the plus minus minus plus. Everybody good there? Okay. Now, the one for sine is kind of the same way. You'll notice I did alpha then beta, but here's how this one works. Okay, this one isn't as nice a trig function, so here's what I do. I write sine alpha cosine beta, and because these two are different, I get to use the exact same operations. So if this is plus, I do a plus here. If that's a minus, I do a minus there. And then guess what goes over here? Cosine alpha, sine beta. So each one gets its term. You'll notice that the alpha and the beta are always in the same order. It's always alpha then beta, alpha then beta. First one, then the second one, all the time. Okay? I don't care how you keep these straight. If you've seen trigonometry before, if you've seen these and you had a teacher that taught you some way to memorize them, I don't care how you get them memorized, but you have to have these memorized. Okay? These are called the sum and difference identities for sine and cosine. Okay? You'll see them on the test on Friday. You will see them on a test in 1060. You will see them on the final on 1060. I can almost guarantee it. Okay? All right. So here's how this works and why we'd want to know this. Because we can use trig values that we already know, like cosine of 45, sine of 30, different things like that. We can use common angles that we're already aware of to build new ones that we don't know exactly what they are. Okay, and that's actually kind of cool that we can do that. So let's take a look at this right here. This says the cosine of 15 degrees. That is not a common angle, but I can do this. I can rewrite it in terms of a couple of common angles that I know. Now, what would the easiest way to rewrite 15 degrees be in terms of angles that we already know? Yeah.
45 minus 30.
45 minus 30. That work? Okay. Did anybody think, hey, I'm going to use cosine of 60 minus 45? Would that work? That would. Okay. If you apply these identities correctly in both situations, you're going to get exactly the same answer. Okay. So here's what we're going to do. When we do this, this is a cosine. So I'm going to break this up and I'm going to do the cosine of, whoops, got to write them in the right order. Cosine of 45, cosine of 30, plus or minus? Plus, okay, because these two are the same. This has to be the opposite operation. So I'm going to write plus. And then this is going to be sine of 45, sine of 30. And then I need to know these quantities right here, which hopefully are pretty easy because we memorized those, didn't we? And this is why memorizing that stuff from the last chapter, why it comes in so handy, because you can do these very quickly. Cosine of 45, square root of 2 over 2. Cosine of 30, radical 3 over 2. Sine of 45, square root of 2 over 2. And sine of 30, 1/2. Okay? The nice part about this is we're almost always going to get a common denominator. So we end up with radical 6 over 4 plus radical 2 over 4. So my answer is radical 6 plus radical 2 over 4. And there's the answer. Now grab your calculator. So I'm going to clear this off. I'm going to go to the home screen. I'm in a trig class, so the first thing I'm going to check is I want to be in degree mode for this particular problem. I'm going to go to the home screen and I'm going to type in cosine of 15 degrees and I'm going to hit enter. Then I'm going to check and see if what we got, this is an exact answer. It's got two radicals in it. We're going to see if we actually got the right answer. So I'm going to start a set of parentheses. I'm going to do the square root of 6 plus the square root of 2, close the parentheses, divide the whole thing by 4. And look at that, right out to, looks like 10 decimal places, got the right answer. Good there? Any questions? Okay. Guess what would happen if we did this? So if I were to write this, so this would be cosine of 60, cosine of 45, plus, right? Sine of 60, sine of 45. Guess what I get? I get exactly the same thing. We'd have a radical, I think it would show as radical 2 plus radical 6 on the top. But that's okay because it's addition and that's commutative. Okay? So it'll work either way. Any questions there? Okay. Turn your attention to this next example right here. Okay. Now, on this one, we're looking for the sine ratio of pi twelfths. Now, if you want to rack your brain and think, okay, pi twelfths, how can I make a pi twelfths? If you want to go through and say, anybody know off the top of their head? Is it important that this is measured in radians? No, because the answer to this is a ratio. So if you like racking your brain about problems like this, or if it said 7 pi twelfths or something like that, and you wanted to think for a while and figure out what that is, that's totally okay. With enough practice, you could realize that this would be pi thirds minus pi fourths. Wouldn't it be? Because this is going to be 4 pi twelfths minus 3 pi twelfths, and that's going to give us pi twelfths. Good there? Now this one's a little bit easier. This one's going to be pi fourths plus pi thirds, because that would be 3 pi twelfths plus 4 pi twelfths. That would be 7 pi twelfths. Do you want to spend time racking your brain about how to combine different angles of pi in radian to figure out what this angle is? Or would it be better to just figure out, hey, the answer is a ratio. It doesn't matter what angles we're using, whether they're degrees or radians. We just have to represent the right thing. So pi twelfths, let's convert that. 180 over pi, those cancel. 12 goes in here 15 times. So even though it doesn't look like it, this is the sine of 15 degrees. Now, just for the heck of it, let's do this one using 60 minus 45. So remember how this goes. Cosine's good because we get to use the same one twice. This is going to be the sine of 60, cosine of 45. What goes in between these? Because these are different, this sign gets to be the same. So this is going to be a minus. And then this is going to be the cosine of 60, sine of 45. Any questions? There's the identity right there. Okay, remember how this is the way I like to think of it? Because these are the same trig function, this has to be the opposite operation. So if this is plus, that's minus. If that's minus, that's plus. Because these are different trig functions, the operation gets to be the same. So if this is minus, that's going to be minus also. Good? Okay. And then you just need these four quantities. So this is radical 3 over 2, radical 2 over 2, 1/2, radical 2 over 2, and we end up with radical 6 minus radical 2 over 4. And if you throw that in your calculator and you check it, that will give you the right answer. Now, just a warning. Some people will do a few of these, they'll look in the back of the book and they'll say, I get the same answer every time. Well, you won't get the same answer every time, but usually because we're using all of those common angles that are 1/2, radical 2 over 2, radical 3 over 2, and 1, and stuff like that, you're going to get very similar answers. So if we look at the two of these, they're very similar. If we did this one up above, it would have turned out to be radical 2 plus radical 6 over 4. Almost the same thing. Sometimes you'll end up with negative radical 6 minus radical 2 over 4. They're all very similar because you're using the same building blocks. Does that make sense? Okay, any questions there? Okay, raise your hand if you've seen this before. Okay, very good. Then this is just a nice bit of practice. Take a look at example 2. It says just write it as simply as you can. There's the identity right there. If you don't have it memorized, you've got to get it memorized. Cosine, cosine, sine, sine. Notice that the first angle here is the same as the first angle there. Second angle here is the same as second angle there. Is this a cosine or a sine? This is a cosine. Question is, what do you do with the two angles? Do we add or do we subtract? We subtract them because these two are the same. That has to be the opposite operation when we put it in here. So this is going to be the cosine of 60. Now, if this had turned out to be 61, could we find the answer? Not without a calculator. But on this right here, we know the cosine of 60 is 1/2. Simplified to some extent right here because we wrote it as the cosine of an angle, one single expression. And then there's the answer right there. There's the actual ratio. Any questions? Okay, I'm going to make this a little bit smaller so we can still see those up above, although you can see them. Okay, it says simplify there. Certainly not going to be able to get an answer for this one, a ratio for this one, but take a look at what we can do. Cosine, cosine, sine, sine. 3y here, then y. 3y here, y there. Does it fit the pattern? It does fit the pattern. It does fit the pattern. Okay, so this is going to be the cosine of 3y and y. What do we do with them? Add them together. So the easiest way you could write that would be cosine 4y. Okay, would you do the next one, please? Look at that next example, B. Something wrong with it. What's that? The angles aren't the same. The alphas aren't the same. This is a negative pi halves, and this is a pi half. So you've got to check and make sure, first of all, does it fit the pattern as far as the trig functions go? And we're kind of focusing on cosine for the time being. Cosine, cosine, sine, sine. That's good. But they have to be in the exact same order. So this is going to be negative pi over 2, positive pi over 2. Pi fifths, pi fifths. So we're in good shape with the pi fifths, but not right here. So stop and think. I think Noah knows what to do. Do you?
Maybe.
He says maybe. That doesn't sound very confident. What do you think?
I think it's a plus or minus pi half.
Put a plus or minus right here?
No.
Or that you could do either one.
Yeah, something like that.
So up here, you could do a plus or minus alpha. It wouldn't matter
Yeah,
whether it's a
plus or
positive
minus
alpha or a minus alpha. That is true on that particular trig function, but I need to know why. So here's what Noah's saying. It doesn't matter whether it's minus or plus.
Oh, wait.
You could just make it positive if you needed to. And that is true if it's a cosine. If that were a sine, that's not true.
I know.
Nathan, why?
Probably isn't it that inverse, or no, not inverse.
What are they called? Odd even identities, right? Odd even identities. So is cosine an even function or an odd function? Cosine is even. So does it matter that this is negative? Nope, we're going to get the same cosine value if we go in the negative direction as if we do when we go in the positive direction. So we can simply ignore that if we want, or just make that a plus on this one. If that had been the sine of, and it wouldn't be on this particular one, but if it had been the sine of negative pi halves, what does an odd even identity allow us to do here? Yeah, we pull that out front, right? Okay. Now does it fit? And it's the cosine of pi halves, pi fifths. What do you put in between there? You put a minus in between there, and then you've got to go figure out, well, gosh, what's a common denominator there? So this is going to be 5/10 minus 2/10. So that's going to be the cosine of 3 pi tenths. Not something we could figure out without using a calculator. So if it did say find the actual numeric answer, what is the cosine ratio? You'd have to throw that into a calculator. Any questions? Okay, we did the cofunction identities in a previous section. Let's take a look at this one right here, and it says verify. In other words, prove that's an identity. Prove that that's an identity. Again, we're working with the cosine. So I'm going to take this side. We're verifying. Everybody agree this is the more complicated side? So let's rewrite it. What am I going to write? Cosine of pi halves, cosine of beta, plus or minus? Plus sine of pi halves, sine of beta. What is the cosine of pi halves? 0. So what's 0 times cosine beta? 0. What's the sine of pi halves? 1. So this is just 1 times the sine of beta, and that is sine beta, and there we go. So what's the rationale for this? Some difference identity for cosine. The rationale for this is just values of trig ratios. And this is just simple multiplication, right? 3 little steps and we verified the identity. Okay, so that's a different way of thinking about those cofunction identities that we already know how to use. Okay, any questions? Okay, read that next sentence right there to yourself. Okay, I will absolutely guarantee that you will see problems like this on an exam and most likely on the final exam in 1060. They put them on there all the time, okay? And for some reason, people struggle with these, and I think it's because they don't think about them and don't practice them the right way. Here's the way I'd like you to do this, okay? Notice that right here is the beginning of a difference identity for cosine. So here's what we're going to do. I'm going to write down that this would equal cosine alpha, cosine beta. Those are the same, so it's got to be a different operation. So I'm going to write plus sine alpha, sine beta. Everybody good there? Okay. Then this is what I'd like you to do. They give us information in the beginning about alpha, and they give us information about beta. So let's read this right here about alpha. It says the sine of alpha is 24/25 and alpha is in quadrant 2. That is a huge chunk of information. So in red, I'm going to draw a picture for alpha. So here's what alpha is going to look like. Alpha is in quadrant 2. I've drawn it in quadrant 2. And then something that I mentioned numerous times in chapter 4 is going to come up again. This is the opposite side, and this is the hypotenuse, right? So this is 25, and this is 24. Whoops. I'll make that a little bigger. Hopefully it sticks around this time. 25 and 24. I need to know what side this is, or what the length of that side is right there. Okay? How can I find that? Pythagorean Theorem. Okay? Now, it is not, you don't add these two together when you square them. You add these two together when you square them. So you get x squared plus 24 squared equals 25 squared. So you get x squared equals 25 squared minus 24 squared. So you get x equals, what is it? Okay. X squared equals 49, so that means x equals 7, correct? Okay, put that number right here. Don't look at your neighbor's paper, just put that number right here. Peyton, F for the day, looking at Brandon's paper. Anything wrong? Logan? It better be negative. If you get that wrong, not only have you ignored something that we practiced and said repeatedly in chapter 4, now that we're just using stuff like that and not really focusing on it, you're going to get the answer wrong. And you're going to look in the back of the book and say, my gosh, why am I getting the answer wrong every single time? Okay, and it's because all you're doing wrong is not realizing we went back and up in quadrant 2. That means the x-coordinate's negative, y-coordinate's positive, hypotenuse is always positive. So you've got the adjacent side identified correctly, opposite and hypotenuse. Could we figure out everything we need about alpha? We could, okay? I'm going to change colors now. Let's take a look at beta. It says the cosine of beta is 8/17 and beta is in quadrant 4. So the cosine of beta is 8/17 and we're in quadrant 4. So I'm going to change colors again. I'm going to draw a picture for beta. It's in quadrant 4. Cosine is 8/17. This is 8. That's 17. I need to know what this one is right here. I'm going to say y squared equals the hypotenuse squared minus the leg squared. I'm going to skip a couple steps in the Pythagorean theorem. Is that okay? So if you rearrange it, it would always be the hypotenuse squared minus a leg squared. That should equal the other leg squared. Okay? So that's going to be y squared equals, this is 289 minus 64, correct me if I'm wrong, but that's 225, which when I take the square root, I get 15. And then I'm going to put this number right here, and we're not going to do anything silly because we've gone over this, and we're not going to make this mistake on an assignment, on a quiz, or on a test, or when we get into 1060, right? That is negative 15. Do I have all the information I need about beta? So here's the cool part. Look at this. I need to know 4 values, just like I did up above, in order to figure this out. I need to know the cosine of alpha. So let's come over here, look at alpha. What's the cosine of alpha? Adjacent over hypotenuse, negative 7/25. Cosine of beta. Look at beta. I need the cosine. Cosine is the adjacent over the hypotenuse, 8/17. Sine of alpha. Let's look at alpha. That's going to be 24/25. And I need the sine of beta, so we look over here. Again, really important that I got that to be negative 15 because that's negative 15 over 17. And now all I have to do is go through and do some arithmetic. Everybody stop and look up here, please. Look at what we did. I used alpha to draw this picture, and then I looked at the picture and I figured out what these alphas were, or these values containing alpha were. Okay? Beta, I drew a picture for beta, and then I looked at the picture and came up with this. Do yourself one last little double check to make sure that you got this right. Okay? Sine of alpha is 24/25. Come over here and find the sine of alpha. Did we put it right in the formula? So if we did that right, did we probably get our picture right? Probably, okay? And cosine of beta is right here, and it matches up with the information that was given, and yet we pulled it from the picture. If you can do that, you're probably going to get the answer right. The other cool thing about this is, notice this is negative 56, and let's see, what do we end up with here? This is 425, is that right? Notice that the other one turns out to be negative. The denominator is 425, so we get that common denominator that I was talking about. And negative 24 times 15, what is that? 360. So I end up with negative 416 over 425, and that right there is the answer. Now, if you wanted to figure out what angle alpha is, you could, using inverse trig. If you wanted to figure out what angle beta was, you could, using inverse trig. And then if you wanted to put the two of those together by subtraction, take the cosine of that, you would get this number with a tiny bit of error, okay? Because you'd have to round the answers that you had there, unless you stored them in your calculator like I taught you how to do, okay? Any questions? Okay, we did a whole bunch of stuff using the cosine identity. I should probably put more on there. Ooh. And we're going to change that one. We're going to change that one to sine. But we'll pick these up tomorrow, okay? Just so we use a couple of the different ones. Yeah, you're going to turn in 5.3 tomorrow. You've got enough you could get started on 5.4. Go ahead and start on 5.4. Thanks.